Welcome. In this video I will show you how to calculate the packing efficiency or packing fraction of the 4 closed packed structures. These 4 closed packed structures are the simple cubic, body-centered cubic, face-centered cubic and hexagonal closed packed structures. Yeah, let's just start it. So I will start with the simple cubic structure. Just let me write it down. So if you remember, I already showed this in one of my tutorials. We have a cube and this is the unit cell, and each corner is occupied by an atom, like this. And then we know that therefore the number of atoms is 8 times 1/8. So it's just simply 1. And now we can calculate the volume occupied by the atoms. This was capital W, and this was like n times the volume of each atom. Then now I just use R for making it simple, and since n is 1, we just simply get back the volume of a sphere, like this. And then we have the volume of the unit cell, which was capital V, and this is just simply the cubic A. And then we also know that the lattice parameter is equal to 2 times the atomic radius. So all these details come from our previous calculations. You can find them in the description. So what the packing efficiency says, that we have to see what is the ratio between the volume available, or the volume of the unit cell, and the volume occupied by the atoms. So basically we just divide the W with the V. So in our case it's just 4 pi over 3 times r squared divided by 8 times r squared. 8 comes from the 2 of the third power, 2 to the third power, so we just use the third power of the 2r. And then we simply see that we can simplify by the cubed r. So we just left behind, this is 3. So 1 over 2 times 1 over 3 times pi, which will be pi over 6, and this is roughly 0.52, which is 52% of efficiency. It's not so good. So let's move on and just put one atom in the unit cell in the middle. So we basically create the body-centered cubic structure. So let me draw it again. So basically this should be a cube and not a prism, but so there is one in the body center, just to make the 3D effect, and we have the other guys at the corner of the body. So we can start to calculate or count the number of atoms. We have 1 in the middle plus the rest at the corners, right? And this will be 1 plus 1. So we have 2 atoms per unit cell. And therefore the W will be slightly different. So now we have 8 pi divided by 3 times r squared. And from the previous lectures we know that this is the same because it's a cubic lattice, and we know that the lattice parameter is slightly different. So basically 4r divided by the square root of 3. And then we can calculate the efficiency again with the same formula. So let's divide the volume occupied by the atoms with the volume available, so we can see how efficiently we fill up the volume with the hard spheres or balls. So as I said, we have 8 pi over 3, and then we divide this whole thing with the following. So we just use this expression here. So 4r square root of 3, and this is to the third power, right? And we will see that we can immediately get rid of the r to the third power, and then we will left behind something similar like this. And we see that 4 is on the to the third power and the square root of 3 to the third power. So basically we will have something like, if you know that this is a bit tricky, so you have this guy here, so this should be like this, and then this should be like this, and also like this. So you can get rid of these two guys here, 1, 8. So you have pi times square root of 3 and divided by 8. And then this will be roughly 0.68. So P equals 68%. So if we put one atom in this simple cubic structure and make it into body-centered cubic, we increase the packing efficiency from 52% to 68%. So 16% better. But these structures are not the best in efficiency. So we will see that there are better guys. So let's move to the face-centered cubic structure. Face-centered cubic. So let's just draw our usual cube, the unit cell, like this, and then make it 3D like. So first let's start with the face atoms. So we have 6 faces on the cube. 1, 2, 3, 4, 5, 6. I just connect those to make them more visible. And then we have the 8 corners, right? 1, 2, 3, 4, 5, 6, 7, 8. So number of atoms first. We said that we have 6 faces. Each face gives us half atom to the unit cell, and then we have 8 corners, right? And they give 1/8. So 1/8. So this will be 3 plus 1. Very simple. It is 4. N equals 4. Then according to this we can calculate the we can calculate the volume occupied by the by these 4 atoms in the unit cell. So if you see that now we have twice as much atoms in the same volume, so you will expect better packing efficiency as compared to the body-centered cubic, and also you expect better as compared to the simple cubic, but of course not 4 times more. But going back to this part, we have something like this. This is still the same boring formula, and then we can agree that this is the following. So let's do the same calculation. So 16 pi over 3 r squared, and then let's divide it by 4 square root of 2 r squared. Now we see immediately that we can simplify with the r squared, and we will left back something like 16 pi times, you can see 3, and then you make the power, so this will be 64, and then 2 times square root of 2, and then square root of 2, and then let's divide it by 3, and we simplified with this, so 32. So if we just simplify with this thing, we see that we have square root of 2 times pi divided by 6, and then this will be equal to 0.74. So P is 74%. It's much better. It's much better. If you see the simple cubic, that was like half of the unit cell is occupied, and then here is like 2/3 of the unit cell is occupied. So it's much better. And then finally we go to the last closepacked structure. So hexagonal closepacked HCP. So let's first draw the unit cell. So we have the upper part, and then we have the bottom as well, and then of course as usual. And if you remember, then we have 3 atoms in the middle. Let's connect them, and then 1 atom and 1 atom in the base, and then each corner has 1 atom sitting there. So the N is, let's start with the full atoms, 3 full atoms, so we don't do anything, and then go to the smaller contribution. We have 2 half atoms up there and down there, and then we have 6 times 2 times 1/6 atoms. So what we have here is 3 plus 1 plus 12/6 plus 2. So in total we have 6 atoms. And then we just use this 6 in our usual formula. So this will be 24 pi divided by 3 and r squared, just to make it simple. This is, and then the volume is a bit more complicated because this is not a cube, we can simplify the structure to have a prism, but I make the things a bit more difficult. So this is this can be obtained from any mathematics books, or just Google it. So if you remember, then A was this edge length and C was the height of the cell, and we should know that we have to know the ratio between A and C. So I showed it already in one of my previous lectures that the C over A in ideal case is square root of 3 divided square root of A divided 8 divided by 3, and from this we can get to the R, so or the C, and we can say that the C is 4 times R times 2/3 under the square. And we also know that A is 2R. We have the 2 atoms sitting on the edge. So we start and just simply calculate the ratio again. So we have 8 by R squared, and then we divide this by this complicated formula, and we have 2R squared, because this is A squared, and then we have this 4R, this is the C term, 2 over 3 and square root. So I don't make any simplification in the denominator. No, sorry, I make only simplifications in the denominator. So we will see that this parenthesis will break up, and we see that 4 here, so we can start with 3 times square root of 3, and then we have this 4R squared, but we immediately get rid of this. So this is 1, this is 2, and we continue to write our equation, and then we just left behind with this. So basically what we have is pi, because sorry, I left out something. Yes, the 2R, because we got rid of this and this here. So I think it will be pi divided by, this is nothing, we have 3 square root of 3, and then 2 over 3, and let me continue down here. So basically we just get rid of some stuff here, and this is 3 times square root of 2. So this is 74%, and surprise surprise, they are the same as the, or this is the same as the hexagonal structure. No, the hexagonal structure is the same as the face-centered cubic structure regarding the packing efficiency. And in a later video I will tell you why, but these two lattice structures share a lot of similarities regarding a lot of things. So I think this was all. These are very simple exercises, and all you need to know is basically how to calculate the volume occupied by the atoms within the unit cell, and then you just calculate that volume, and you calculate the volume of the unit cell, which is in most of the cases just a simple cube, so a to the third power, and you divide the two quantities with each other. And then you see that you had some volume, and you occupy some volume with these hard spheres or balls. So how much do you occupy? So I hope it was useful, and I hope I did not make any mistakes, but seems more or less okay. So see you in the next video. Thank you for your listening.